energy is very high, and the materials, we cannot make any kind of chamber or any kind of device which can hold that plasma state, because it is having very high temperature. Any material with that temperature will not sustain. Okay? So it will melt down very easily. So the basic idea behind this is that the plasma state is having very high temperature. Since it is having very high temperature in the order of, if you consider that in the case of sun, it is 10⁻⁷ Kelvin. So almost that much of temperature is required to have that plasma state, and making that high kinetic energy. Nuclei which we are using for this fusion reaction. So that much of temperature no material can sustain. Okay, so that is the problem, one of the main problem which we have in this thermonuclear fusion reactors. So we cannot use any material to confine this plasma. Okay, then we have to do some other approach. We have to do some other kind of techniques to confine this plasma state, and one of that is the magnetic confinement. Magnetic. So in this magnetic confinement, what we do, we have this magnetic field, as you can see from this figure. We have this magnetic field in such, as you can see in this figure, we have some particular kind of magnetic field. The field is, we arrange the field in such a way like it is number of fields per unit area will be very high in this range at the ends. Okay, and that will be smaller in the middle portion. Okay, in such a way that the field is arranged, that is made. And if any particle which is coming to this field, if any electron, for example, is coming into this field, and this field, in this field, if you make it a perpendicular entrance, for example, electrons are coming in this way. So if it is coming this way, then it will be having some kind of rotating motion or helical type of motion like this. It is inside this magnetic field. And then when it reaches here, we have a very strong field here. And if you consider that this particular electron, which is in this particular point at the end of this magnetic field distribution, that will produce some different scenario in such a way that it is propagation just will become opposite in that. Okay, so here when it reaches here, it just repels back. So I will draw it in a different color, right? So when it reaches here, from here it will come back like this. Again, it will show some helical kind of path, and it will come back. When it reaches here again it will go. Okay. When it reaches here, again it will come back. So the electron or the ions, which is in that plasma state, that will be confined in this magnetic. Okay. So this is magnetic confinement. So the field, we have made the strength of the field and all those things in such a way that we have more number of field in this region, in these two ends. Okay. And this so that when the charged particles comes to this point, its direction will just reverse. Okay. So you can calculate that direction by using that F equal to Q B cross B relation, that force. So it depends on what is your V and B. Then you take that cross product. What is that propagation direction. For velocity components, you check, and what is that B component in this range. And if you consider these two, take cross product, then we will get just a minus of what is just here. If you, for example, if you consider V equal to, I am talking about a point here, somewhere here, okay, this point. So that V will be, for example, that I will take Vz k cap plus Vx I cap. So which means that it is opposite to that Z. So if you consider that axis like this, that axis we have to take X, Y, and Z axis we have to take. So let's say this is your Z, this is your X. In X direction we have that propagation, and we have Y. So we have Vx components, Vz component, and so the velocity will be Vz. Oh, this is in. So I take this is in Y, and this is X. Or I have to take, I think, Vz is in here. Okay, so that will come my B as Vx I cap plus Vy j cap. This is my field direction, so I am applying that field in the Z direction. Okay, so I mean at this point. At this point. So this will give force equal to Q into Vx I cap plus Vz cap. This has to be cross producted with Vx cap by j cap. So this will be. So if you take this cross product and all those things, just check that what will happen to that I cap. Okay, I cap only check that here we have Vz k cap, then we have V by I. So if you take these cross products between this V X, okay. So what will give you I into I? So I cross I, then K cross J. You take these two. These two you take. So you have some constants here, some products will be there. We have to consider that I. Why we have to consider I? Because our velocity in that X direction. I will take. Sorry, this is X, and this is my Z. So that velocity in that X direction that we have to consider. So in that case, velocity in that X direction, which is denoted by this I cap. X positive X direction. So it means that this is my I cap. So if you take this product now, these two products, so minus Vz into minus, that will come plus Vz Vy, then K cross J give me minus I. So what happens here is that the I, initially I was having velocity component Vx in that X direction. It is my X direction. So that is just reversed. Minus I. Minus I means that this is my minus I. So at this point, you consider this point where you have a magnetic field and velocity like this. Okay. So the components will be minus Vz cap. That Z is coming. So the velocity component, which means that the particle is coming from that backward. You consider the screen, backward of the screen towards you. So it is like that kind of motion. So then only you get like this. So it is coming from backward of the screen towards you. So in that case, we have minus Z direction. So it is coming from this direction. Okay. So we'll be having, suppose this is your plus Z. So backwards. This is your X. So it is coming, suppose if this point is considered, if it is, so then it is coming from reducing that Z. So from that Z it is coming back. So it is in the minus K direction. Okay, that's why we put here. Yes. Okay. Then Bxi, so it is having some component in this positive X direction. So that is the helical shape. So it's like it is moving like this. So at this point I'm saying. So some X component, and from that Z it is relating in this direction. So it is minus. Okay, so that is at that point we are considering this particular point. What is that velocity? And then we have that magnetic field component also, Bx I cap, that is in that this direction. Then minus By j cap, which is in that perpendicular direction. Like the big field will be like this. Y, X. That is experienced by this particular electron or the ion, whatever the particle it is. Okay, so that is having both this Bx I cap minus By j cap. So minus By j cap means it is reducing that height, that magnetic field. Bx I cap. So the components in this position is that like this and this. We are having only this kind of we do not have that perpendicular. We are not considering these components here. So these two are perpendicular. And then we have that particle somewhere here, and its velocity is in this direction. So it will be like this. It will be having both that Z component as well as, because it is helical. Okay. Anyway, you just understand that basic idea that we have here the particle which will just reverse its direction. Here also we have just just reverse its direction. It will act like as a magnetic mirror. Okay? So the particle will be coming in this direction, and when it reaches here, it will be reflected back and coming back. Then when it reaches this end, it will again reflect back. So the magnetic field, because of this magnetic field arrangement, the ion and as well as the electron will be confined in this range. Okay? So this is the basic of that magnetic confinement. Then if you consider this particular case, the problem is that we need the magnetic field arrangement in this much of fashion. This field has to be very much carefully arranged to make this confinement. So here we do not need any material. So electrons or ions do not interact with any material. They are confined with the magnetic field. Okay. So then if you consider another type of confinement apart from this, that is called as inertial confinement. Inertial. So here what we'll do, we will make that pellets. First we have to consider pellets. Pellets of deuterium plus tritone, okay, neutron plus tritone that we have to make. And then this two, we already discussed about pellets. We have to make that powdered form and make it to some solid structure by applying some pressure. That is the pellets. We already discussed about in the nuclear fission reactors. So that pellets we have to make with this deuteron and tritone. Then suppose this is your that sample, that pellets. Then we have to apply some high index laser field, high index light beam, apply to this pellets. Normally we use laser radiation from the lasers you can use. So from this laser source, we apply electromagnetic radiation, very high intense light beam to these pellets, which is made up of this deuteron and tritone. And when this highly intense light hits on these pellets, the plasma will form. Because of these pellets get all those energy from this radiation, and this radiation from all those energy, this will be very small quantity. So that energy will be absorbed by this sample, and it will form the plasma. Okay. But this plasma will be within some nanoseconds time. It's not a very large time scale. So for some nanoseconds times, you'll get that plasma. So within that time, you have to have that fusion reaction. That is another method. So that is called as inertial confinement, where we have this pellet of neutron plus tritone, and we have to apply some highly intense radiation from laser source and make the plasma state for those mostly used, widely accepted method, which is called as the modern. The modern, it is also the modern method, which is called as tokamak design. Tokamak design. This is developed by some Russian scientists. This tokamak design is normally using in mostly different fusion reactors. Still, it is on development stage. So we do not have a complete structure because we need more and more efficient nuclear fusion reactions. So people are trying to improve the designs. But basic design of this tokamak is that we arrange number of coils. Just draw here. Let's say this is your so it is basically like a torus structure, and you have that coils here. Let's say these are your coils. These coils are uniformly wounded. So this is anyway. So this will be there for this entire range. This should be uniformly wounded. Okay. You draw that. You draw it. So it will be like this. completely. Okay, so what happens when you apply some current through this coil? In this coil, you can use some detection method or those things. But when there is current flowing through this coil, it will produce some magnetic field, and that magnetic field will be here in this range inside this coil. And that magnetic field is called as toroidal field because of this toroid kind of structure. We can see much more here. Here, from here. Okay, so this is the uh, circular coils, okay, and which are carrying this current, and that will produce the field which is called as toroidal field. That toroidal field will be in this direction. Okay, you can see this yellow. So this is your toroidal field. Now you consider any charged particle inside this field. Okay. If you put any charged particle inside here, here some electron, or here we. So this electron will experience that force Lorentz, that F equal to QVB force, that force. So that because of that force, because of that magnetic field, force will be experienced by on this electron or the ions. So they will revolve around this in a circular path. Okay, so they'll be moving like this. So if this electron is here, and it will be moving. But there is a problem with it is this design. We have more number of coils inside in this interior regime. You consider this area, you have more number of coils, or the coils, that concentration is more in this range of coils per unit area. If you take same area on the outer portion, you will get less number of coil, because this circle is smaller as compared to this one. Outer radius is smaller. So here we have more density, or we can say that number of coils per unit area is larger in this interior region as compared to the outer section. So the magnetic field will not be uniform this time. So the electron which are revolving around this, there is still probability that this can hit on these circular coils, or where you can use some different shielding, but still it will hit on that wall. So because of it is a high temperature, high energy, that wall will get damaged. So in order to avoid that, we will insert some different coils again inside this design. So we have additional coils inside here. Show you the picture. So we have additional coils like this. These coils will control that electron circular path, so that the electrons will not hit on that walls, and that this particular coil will make some current, some magnetic field. Also, these electrons which are moving in this coil, that the because of that toroidal field, that also make magnetic field because it is charged moving, electrons are moving, so that will also make some current, and associated magnetic field will be there. Together with this magnetic field, and those which is from this line, current carrying the line, that also uh, both of them will contribute some kind of spinning action like this, for those electrons, so that electrons will not touch on that walls. Okay, so there will be electron which are propagating in this direction due to the toroidal field, but still it can hit on those walls because of this number of coils per unit area in the interior and exterior of the portion of that design, which is not equally distributed. so that it can still hit on those walls. But because of this additional coil that we put, and the magnetic field produced by these electrons, which are or the ions which are revolving, which are moving in that circular path, that together, this coil, magnetic field produced by using this coil as well as that electron path itself, that will make some kind of spinning action, some rotatory action in this direction, like this, so that the electron will not touch on that walls, and the electron will so that the charged particle electron and ions will be confined in this particular structure. So I will explain that again in this. So this is your toroidal magnetic field direction that I have already. And this one is your this yellow colored one. This is your colloidal magnetic field that is coming because of this position control coils. You can see this blue colored coil. Okay, because of that, as well as that electrons movement itself creates magnetic field. Together, that will make this colloidal magnetic field. So it is having some kind of spinning kind of direction that you can see from here. Direction is like this. So what actually happens? It will be having this much of diameter for that electron, which is revolving. So this will be propagating in this direction because of this toroidal magnetic field. It will be propagating this direction. Along with that propagation, there will be a circular motion like this. And this circular motion, which is having some kind of radius from this axis, that radius is controlled by this magnetic field produced by this position control coils as well as the electron itself. Okay, so that electrons will be going like this in such a way that it will not interact with these walls. So this is basic of that tokamak structure. There are still more components of those things, but this is a basic idea behind that tokamak structure. So we have coils to confine that plasma in this particular range. Okay, this is normally nowadays normally used using technique. Currently, it is still using technique, and people are trying to improve its structure and efficiency, all those things. Okay. So this is the basic structure of that tokamak. How the plasma is confined inside this region. So this is your plasma field. The electrons or the ions here. So this will be having this kind of propagation as well as rotation motion. So plasma will be going like this actually. About that axis. So it will not hit on this wall because it is restricted up to this range. That spinning action is restricted up to this range. So it is well protected from this wall because of this position control coil and that particular field, which is called as colloidal magnetic. So this colloidal magnetic field make that circular action, and toroidal magnetic field make this circular action, that is the propagation itself. When the electrons and confined in this particular, okay. Then they can interact. That ions have nothing but yes, they can, if they have enough energy, they can cross that potential barrier and interact each other. Still, but we need more current to have this magnetic field production for this confinement and all those things. We need a very high temperature has to be made inside this this particular design for that plasma state. So all those things require energy, and if you have 100%, suppose if you take that 100%, that is energy given to that system for all these confinement and other operations. But the fusion, after fusion, we will get some energy, and when we measure that energy, which is only 70% of what we have given. So still we do not have that fusion reactor. So it is in still in developing, and it is most ongoing process, which is in the ITER, International Thermonuclear Experimental Reactor, International Thermonuclear Experimental Reactor, ITER. Okay. So, which is a collaborative work. Okay. So, different research will be happening in different countries, and together they will combine all those experiment results. France, it is in France. So ITER, International Thermonuclear Experimental Reactor, which is still developing. Okay, so it is giving some 70% of energy back. So if we have to improve it again to get a gain. Okay. So this is the basic of the tokamak structure. So we discussed the 3 different types of confinement for that plasma. First one was the magnetic confinement. Second one, magnetic confinement, we need these 2 kind of structure design for this magnetic field. Then there are 2 ends basically. Ends, we have ends here, so that the magnetic field we have to vary at the ends in such a way that it is propagation vector. That direction should be reversed in such a way that we have to arrange that magnetic field and those things. And then we have the inertial confinement, where we have the pellet with D plus T combination, and then we irradiate that pellet with high intense laser beam, and plasma state is created, which will be having some nanosecond time scale, and the fusion reaction has to be happen. And third one is that the tokamak. It is the very advanced and currently widely using technique is that tokamak design. That is still research is undergoing, where we have 2 different kind of field. First one is from that toroidal structure, toroidal field, because of that coils with this blue color. And second one is that from that control roads, that is we discussed with that figure. Okay. So this is the basic 3 different basic idea behind the confinement of those plasma with the high energy. And now we will go to the fusion reaction in stars. I'll just fusion in stars. We will consider that consider separately in sun, because in sun we have one particular nuclear fusion reaction which is dominant. In other some stars which are heavier than sun, we have some other nuclear fusion reaction which are dominant. So we have to discuss that. Okay. So in this particular case, we know that there is no fusion reactors in sun. We do not have any scientists working in the fusion reaction. But to this moment, still the fusion reactions going on and on sun and other stars without having any kind of problem that we are having in our design of those things. So how it is possible in sun to have that nuclear fusion reaction without any kind of interactions? Okay. So that first we will consider where it will happen. If you consider that different layers of sun, if you consider that core region, the core region where we have that fusion reaction will happen. Then we have different zones. So core region will be, this will be almost less than 0.25 of radius of that sun, 25 r, that is the core region. Then we have different zones. I'm not going to tell all those. So we have first zone here, second zone, third one. We have different zones for this. So this one is called as radiative zone. This one. This is. Then we have the second one is this is convective zone. And then after that we have this photosphere. You can refer any associated or figures. Then we have that corona, X region. So all those things happen. So we are not considering these things, but we just have to understand that the fusion reaction will happen inside this core. Okay? So don't think that all those energy is coming out from that nuclear fusion reaction. That is not the case. Here nuclear fusion will happen, then that energy will be absorbed by different materials here in this zone. Then again that light has to pass from to this convective zone, then again to photosphere, then again into corona, and then only that light comes out from that sun, and which will reach in the Earth's surface, and with that much of energy. Okay, so here in the core region, the energy is very large. We cannot sustain that much of energy, and the energy will be reduced from here while that photons and the energy, whatever it is coming out, it is not almost photons. It is not always photons. It is not always photons. It can be some different particles also coming along with that. Okay. But that particles will not come out because of interaction with other particles here, other atoms, all those things, and only photons will be escaping, and the energy will be reduced from the core region when it reaches to the photosphere. Energy continuously reduced, and then only it is coming from the surface of the sun, and it reaches Earth, traveling very long distance. So the energy which is reaching in the sun, which is very small as compared to that whatever it is produced in the core region, and also that core region, the fusion reaction will be happening sometime before some if you consider the time frame. Okay, if you consider the time frame, that suppose one photon is coming from the sun and which is reaching in the Earth's atmosphere, Earth's surface, that photons will not be generated at that moment. It will be happened sometime before. The fusion will be happened a long time before, but the photons will be this energy. That energy will be absorbed by different materials. Different scattering process will happen, and different kind of processes will happen in the sun's atmosphere, and then only that photon is coming out. So the fusion happens, then after that all this process happens, then only that photons come out, and then it will reaches in the Earth's atmosphere. So all this will take time. So don't think that the fusion happens at the same instant that photon is coming and hitting on the Earth's surface. That is not the case, but it is happening sometime before, and after that only that light is coming and falling on. Okay, so if the sun has disappeared, if the sun disappear from its position, still we will get some photons. We'll get some energy for some time. Okay, so we will not notice that it is sun is not there. So it will take time. Even if you consider that gravitational force, all those things, it also takes some time if the sun suddenly disappear from its position. That gravitational waves that will take some time to reach in the Earth's surface. Then only we know that sun has come. So those things are there. Some interesting facts. You can look up different videos, all those things. What is the size of sun? What is the distance between sun and Earth surface? How much time it actually take that photons to travel from the core region of the sun to the Earth? How much time it will take, so that we will understand when that photon generated and when it is going to reach in the Earth's surface. Okay? So it is going to take some time to reach. It is not a quick action. It is not a simultaneous action, but the photons are just created and immediately it is coming to their surface. That is not the case. Okay. So how this is happening in this sun? So we already said that the temperature in this sun's core region, that is around 1.4 into 10 to the power 7 Kelvin, that we already discussed. And if you consider that pressure, it will be around 200 billion atmospheric pressure. Compare that atmospheric pressure, 200 billions of atmospheric pressure. Okay, so it is very high, very huge pressure. So why? Because the concentration is very large. Concentration of these ions, that whatever the nuclear fusion, that nucleus, that is very large. Fusion, for example, if you consider that proton and neutron, their concentration is very large. Okay, so because it will make that very high pressure situation in the core region of the sun with a very high temperature. Okay. So all these things will contribute in this fusion reaction. And the simplest one we can take is that one proton which is interacting with another proton in this condition, that high temperature and pressure, all those things, and that will make this will create H21 plus this is and one will be having one positron. Then along with this positron, we will be having that electron neutrino. Okay, positron with the neutrino, electron with the antineutrino. Remember that. And some energy, plus energy. Energy will be also released. So this is one of the possible reaction. This is protons are rich in sun. So this proton, one proton, another proton will combine, and it will produce one neutron here. Okay, it's nothing but your neutron. So this neutron plus one positron plus one electron neutron. So when positrons are created here, so we can see that this is one proton, and here we have this is one proton reacting each other. So here we have basically one proton and one neutron. Together with that 2 is the mass number. So one proton and one neutron here, and when it make that neutron, it will produce this positron, that is n proton p converted into one neutron plus positron. So you know this reaction, p to n plus e plus e. So this is what is happening inside. Okay. So this is the one of the possible reaction with this light nuclei, that is proton. But there is one problem with this reaction, because we have a beta decay process here. Since there is beta decay process, this is a as we discussed earlier also, this is not a quick reaction, or we can say this is a weak reaction. This is not a strong reaction, I should say. So this is not a strong, this is a weak reaction or weak interaction. Weak interaction. Weak interaction. So because it is a weak interaction, it will take almost long time. So this is almost 14 minutes. This interaction will take at least 14 minutes, or that that much of time. Okay, but fusion reaction will happen very quickly. Okay, we already discussed that. The fusion reaction, we know that 10 raised to minus 20 seconds within this much of time that has to happen. 10 raised to minus 20 seconds. So this is the somewhat time frame of that fusion reaction. So we are restricting or we are demanding this reaction has to happen within this time frame. Then only that fusion reaction will happen. Okay, but since this is associated with beta decay, and since it is a weak interaction, it will take more time. So the fusion reaction with the proton-proton is less probable. Actually, it is less probable because this complete action should happen within 10 raised to minus 20 seconds. Then only we can have that fusion reaction. But still, we have this beta decay process. It will take more time. So we are demanding this reaction that has to be happened within 10 raised to minus 20 seconds. Then only we can have this nuclear fusion reaction. And this particular scenario, which is called as deuteron bottleneck. Deuteron bottleneck. Deuteron bottleneck. Okay. This particular case, which means that we have two proton interacting each other and making one deuteron. This reaction plus positron plus electron neutron. This is the lightest nuclei we are having, and this will happen in sun, this particular reaction. But when you consider this side, we have this beta decay process, and that will happen in some around interval of time, that is in minutes. So we have to make this reaction within this time frame, 10 raised to minus 20 second, or those in that range. Then only that fusion reaction can be possible. So this kind of behavior, this particular behavior is called as this kind of reaction is called as new deuteron bottleneck. Still, it is possible. It is still happening in sun, because the average lifetime of a proton, which is 10 to the power 10 years, or which means that out of let's say 1 out of 10 to the power 18 proton. You imagine that 10 to the power 18. From that 10 to the power 18, we have to choose one. Okay, so 1 from 10 to the power 18 number of protons will undergo this reaction. Okay, that still, okay, if you consider the whole protons, if you consider the lifetime 10 raised to 10 years for these protons, so this 1 out of 10 raised to 18 protons will undergo this reaction. So that will almost make 3.7 into 10 to the power 38 protons, okay, fuse each seconds. So this fusion reaction will happen in 10 raised minus 20 second. Okay, so if you consider that time, and if you have 1 out of 10 raised to 18 protons which are undergoing nuclear fusion reaction, then you take for 1 second. 1 second means we have 10 raised to 20 here and 10 raised to 18 here. So total around 10 raised to 38 of proton fuse each second. 10 raised to 38 protons fuse each second. Okay, so we already said that this reaction is still less probable, but still because of the huge number of protons, otherwise very high concentration of that protons in that core region of sun, we still have this reaction. Still, this reaction will happen in such a way that 1 out of 10 raised to 18 protons undergo fusion reaction. And if you consider each fusion reaction, which is having 10 raised to minus 20 seconds, then for 1 second, the order of 10 raised to 38 protons fuse for fuse, and we have it will produce this energy in 1 second. So that is the basic first reaction which is happening in the core region. So what we discussed, H11 plus again another H11, that is 2 protons combined together, fuse together, form 1 neutron and 1 positron and an electron neutrino plus energy. Now what will happen to this this deuteron? This deuteron again combine with another proton, and that will produce helium 3. Okay, and we have some other particle, that is gamma. This is also with some energy. Energy release will be there in each fusion reaction. Now this helium will not go and fuse with the proton because lithium 4 is not possible. Okay, only helium 3 is possible, but lithium 4 is not possible. So what will happen now? This helium can combine with another helium. Okay, so this helium 3 can combine with another helium, and that will produce 7 beryllium. This is second case, first one. So this will produce helium 4 plus 1 proton plus energy. Remember that this reaction has to be conserved. Okay, so you can count this number of protons and all those things, so that you have to put some number before and after all those things. That you check that. Okay. What I mean is that the number of protons and the number of neutrons in each of these reactions, that should be same before and after reactions. Or there should be some kind of decay process like this, beta decay. Okay. So in this case, how many are there? 1, 1, 1, 2. Okay. So this is okay. The reaction is valid. So I can make this 2 times of this reaction will happen. Okay. Then if you measure this 2, and we have 1 here, So the total that will make the total 3 and 1. So 1 here, 1 nuclear, here 1 proton, here 1 proton and 1 neutron, here 1 proton, then we have 2 neutrons, right? So you have to arrange the reaction because we do not have the equal number here. Okay? So if I put 1 2 here, so here I have 2 neutron here now, 2 times, so 2 neutrons and 2 protons. Okay, here I am having 1 proton, so that will make total 1 2 3 protons, 3 proton, and then I am having 1 here, only 1 proton, and here 1 2 2 protons, so 3 proton, then 2 into 1 neutron, so 2 neutron will be there. So 2 neutrons are coming. Still, proton number is not there, right? Then we have this. So you just check these numbers, okay, and make it in the right form. So then we have 3 plus here 3. So this is 4 here and 1. So here we need 1 2. So 2 times it will be balanced. So 2 times 1 2 and 4 will give me 6. So 2 protons here, 2 protons here, so 4 protons. Here 2 protons this side. Okay, so this will be having, okay, this is right. So 2 times, so this is 4 and 2. Here we have 2 times 2 4. Here 1. So this is not balanced. So 2 times 4, this is what 5. If I put 2 here, so 2 will come here, then it will become 4 more. So this is not 2 plus 1 3, 1 proton, 1 proton plus 2 helium, 3 helium. So check that. Here the total should be 4 proton here, 2 proton, 2 protons, or 4 proton. 4 protons will give me helium for 2 plus 2 E plus. I'm having 2 E plus here, and plus 2 electron neutrino, 2 times electron neutrino. Okay. And plus the energy released in this particular reaction is 26.7. So here I am having 1 proton here. I have used 1 proton here, and here I am having. So here I am getting 2 proton here. So I need 2 proton. So you check this. 1 proton here, 1 proton here. So 2 times this will come as 4 proton, which is in the starting, so that I have it here. Then 4 helium I am getting here, 4 helium. And in between I am having 1 neutron here. And here I am using 1 proton. Okay. So this here I need 2, right? So I need 2 here. Right? So this is 2. It's 2 times. Now it will be fine. So this is 2 times of this. Just check that 2 times proton here. So 2 protons here, 4 protons here. So 2 protons here I'm using. So 2 proton I'm getting. So that will cancel each other. So I'm not writing that 2 protons here and here. So that will get just cancelled. So whatever I have used here, 2 protons, this 2 proton I'm saying. That is already I'm getting back in this reaction. So whatever I have used here, I'm getting back in this reaction. So there will be so there is no loss. And the remaining is that 2 proton and 2 proton here. So this is 4 proton in the beginning. That becomes 1 deuteron, and that deuteron is used here, and that deuteron. So 2 times of that. Okay, 2 times of so two such deuterons are combined with 2 protons. So 2 protons used here. We are getting 3 helium. Okay, so 2 of that. So 2 times 3 helium that I am using here. 2 helium 3, and I am getting helium 4. That helium 4 is my final product that I have given here. And then I'm having 2 proton here that is balanced with these 2 protons. So I am like that. And then energy, and what is remaining, that energy I have written here. And remaining is that this positron and this neutrino, electron neutrino that I have written. Okay, I hope you understood this. So what is how much we used that we have written here, what is produced that we have written here. Remember that this proton which is balanced with this. Okay, that's why I'm not writing this one. And all other things are helium 3, 2 times helium 3 I'm using here, and it is producing helium 4 that I have here. All those things. So this is the one of the possible way of nuclear fusion reaction with this much of energy. This is 26 megaelectron volt, 26.7 megaelectron volt. So 4 protons, this is nothing but 4 protons combining together and forms helium 4 plus 2 positron plus 2 electron neutrino. This gamma also will be there. You can write that. Otherwise, this gamma will be normally come with this energy. Okay, so you can write that also, no problem. Because this gamma will be carried this much of energy. This gamma and this particles mainly. Helium will be having some very small fraction of that. So this energy will be carried out through that photons which are coming. So that's why I told you that energy, complete energy is not coming from there, because some energy will be taken by this positron, then some energy will be taken by electron neutrino, and there is some energy will be taken by these photons, and that photons, this gamma particle, and this again going to interact with other atoms and other different effects, physical effects, scattering, all those things will happen. And then only that energy will come in the form of photons from that sunspots. Okay, so this is one of the possibility, and this particular cycle is called as this particular cycle, this complete cycle, and this is called as PP1 cycle, proton proton first cycle, PP1 cycle. And when you consider the next one, where we will start from that helium 3 plus, sorry, helium 3. Helium 3, we told that here in PP1 cycle, we told that helium 3 combining to form helium 4. But it can also combine with one that helium 4. This is already there. So this is going to combine with helium 4. And that will produce beryllium, beryllium 7, 4. Okay. And this beryllium can again interact with one electron, and that can produce lithium 7, 3 plus 1 electron neutron. This is some kind of internal, reverse process of this inversion. So this is E plus. If you take this side, you will get to this side. If you take E minus, then this also. That is just happening. So this is that electron will be absorbed by this beryllium, and it will become lithium 7, 3 plus electron. Okay. Now, if you consider lithium, this lithium 3, 7, which will react with one proton, and that will form beryllium 8, 4. And this will be along with that gamma radiation. Okay. And then this is very simple. We just proton is getting some number of protons get 4, and total number of neutrons will become 8. The reaction is okay. Then we'll have this beryllium. So don't confuse with this reaction. These are simple steps. So this beryllium 4, 8, that will become 2 helium. 4. Okay. And this particular reaction, this set of reaction, which is called as PP2 cycle. And if you consider that percentage, percentage wise, if you consider almost 85% of time this cycle will happen in sun. Okay. And about 14.9%, many 14.9% will happen this cycle, PP2 cycle. And there is one more cycle, which is PP3, where you have that beryllium 7, that we are this beryllium 7, you know this one I'm saying, this beryllium 7, which is formed in this first reaction. So if you need, I will write that complete here. Okay. So what is that? Helium 3. This helium 2, 3 react with helium 4 in that core region and form beryllium 7, 4. In the next step, what will happen? This beryllium, which will be going and interacting with beryllium 7, 4. Okay. This this is beryllium 7. This will be interacting with proton, and this will form beryllium 8, 4. This reaction. Instead of lithium, converting it to lithium, it is directly going to the beryllium 8 by absorbing one, reacting with one proton, and this plus some gamma, that is photons, and this beryllium 4, 8, which will undergo to the, okay, I will have one, it has to interact with electron, and then it will undergo to that 2 times helium, that last step, 2 times helium 4, 2, plus in this case we have one electron. Okay. So this step, when you write these steps, you can start from that proton itself, where it is changing. Okay. So here, from here onwards, we are going to get that change. Sorry, here, from that three helium formation, from here onwards, in this step, from this step only, from here we have that change for in each PP cycle. So in the first PP cycle, after this reaction, this particular reaction will happen. And second PP cycle, this helium-3 which is formed, which will undergo this reaction, and this set of reactions will happen, that is PP2. And in third process, this helium which is formed here in this reaction, which will be combining with the helium-4 here and form beryllium-7, and these reactions will occur through these steps. So this is PP3 reaction, PP3 cycle, and this particular I'm sorry, this we cannot say this cycle. This is chain. Cycle is different. Cycle means it should rotate. Okay, so this is not cycle. This is chain of reactions. Okay. So this is PP1 chain, and this is PP2 chain reactions. Chain of reactions is happening. This is PP3 chain. Okay. So all these reactions, in if you consider all these reactions, what is the end products from all these reactions? These end products will be same. This is the final thing, final reactions. We can see that this is 4 protons which are combining here. There it is starting. Okay, for all cycle it is starting from here, but from here onwards that is that change is happening. Sorry, this from here onwards that change is happening in each cycle. Okay, so from here, but when you consider initial stage, there is 4 protons which are interacting. So in this here also 4 protons are interacting, and in the final product we have 2 times helium-4 nucleus here, 2 times helium-4 nucleus here. Okay, but we have 1 helium nucleus here. So this 1 helium nucleus which is interacting initially, which is just like as a reactant, that will be in this side. So that will be cancelled by 1 of this helium. So only 1 helium will be left out. So that helium comes here. Then this 2E plus will be there, because first this reaction should happen, and only we get that 3 helium. This reaction and this reaction will happen. So 2E plus I will be having, that gamma also I will be having in all these reactions. So so these 2E plus and gamma will be there, and this 2 electron neutrino, which is also generated in this process. So it also will be there in all these reactions. So finally, what we are getting here is that this 2 times helium, that is only 1 helium will be there, and 1 helium we already used. So used and produced, that will balance each other, and all other things are same. Okay, so that is the basic idea. So all other interactions, all cycles will give me this final reaction, final product. Okay, this final equation. Okay. So basically, it is 4 protons which combine together and produce helium nucleus, positron, neutrino, electron neutrino, and gamma particle. This is what is happening in all these processes. Okay. Now there is another cycle. So in all this reaction, we will be getting 26.7 mega electron volt of energy, okay, as output. But the percentage of or the possibility for the reaction is 85% for PP1 and 14.9 for PV2 and only 0.1% here for this PP3 reaction. So first one is the highly probable and mostly happening reaction. PP1 is the most dominant chain in sun. Okay, and these things are weak. Other chains are weak, especially the third one. And if you consider another cycle which is called as carbon nitrogen oxygen cycle, CNO cycle, this is not very dominant in sun, but it is dominant in heavier stars which are having mass more than sun. So in those stars, this cycle is dominant. This is called a CNO cycle because we are using carbon nitrogen oxygen cycle. So we have carbon which is undergoing these interactions and becoming nitrogen. That again undergoing some reaction which will form carbon again, and it will again produce nitrogen. Okay, then again it's producing oxygen, and this oxygen again produce nitrogen. This nitrogen again give me this carbon, and this is carbon 12, 6. This is nitrogen 13, 7. So what happened here? Mass number has increased to 1, atomic number 1 increased. So one proton must be absorbed here. One proton. There is interaction with one proton. So this proton interacting with this carbon, which will give me 13 nitrogen. Okay. Similarly, if we consider this carbon, which is 13, 6. This nitrogen is 14 and 7. I will just write this first. Then 15, 8, then 15, 7. Okay, so what happens in these steps? So 13, 7 becoming 13, 6. Okay, so something happened here that this nitrogen undergoes some positive, it will emit this positron and then one electron. So if it is emitting one positron means one proton is converted into neutron. This process is nothing but one proton is converted into neutron plus positron plus. So one proton has reduced. So then it will become carbon 13, 6. Then this carbon is again interacting with one proton that will produce 14 mass number. 1 is here. That is 14 will make, and one proton 7. Okay. Again, this nitrogen also interact with one proton, and that will make oxygen 15 and 8. Just increasing mass number by 1 and atomic number by 1. But this oxygen undergoes same reaction as you can see here. That is nothing but E plus and electron. And when this happens, one proton is converting to neutron, so proton number 1 reduced, mass number same, so 15 nitrogen 7. And this nitrogen also interacting with one proton, and this nitrogen release one helium 4 2 and becomes carbon 12 6. This cycle is called as Cno cycle. And even if you consider this case also, what is the total product? The Cno, carbon, nitrogen, and oxygen, they are not reducing. Their amount is not going to vary, because whatever we have started, that is carbon 12, we are coming back to that carbon 12 itself. So total, in this total cycle, nothing to happen this carbon, nitrogen, or oxygen. Their number will be same, because this reaction is conserved, or it is cyclic. That's why it is called a Cno cycle, because carbon, nitrogen, and oxygen's amount will be same. Then where it is different, this proton is used, this proton is also used, this proton is also used, this is also used. So 4 protons are used here. What is the product? Product is one helium nucleus, 4 2, and 2 positrons, so 2 positrons, and 2 neutrons, 2 electron neutrons. Okay, one from here, one from here, 2 electron neutrons, and similarly for positrons. So these 4 protons are used, which made 4 helium, and 2 neutrino and 2 protons, 2 positrons. Okay. So this is the basic reaction. This we observed in all chain reaction also, same reactions. So this also probably gave me 33.6 around this. So sorry, 26.7. This is Cno cycle, that carbon, nitrogen, oxygen is in cyclic form. They are not going to change their amount, but only that 4 protons are used, they convert into helium. So only that is going to happen. Other changes happen. Okay, so remember that only this leg, this one and this leg, this one and this one, this leg absorbing these protons, this is not absorbing, this is not absorbing. Where it is not absorbing protons, there is you are having this positron and neutrino, ejection. Okay, that only you have to consider in this. So what is the proof behind this, all these reactions? We say that nuclear fusion is the reason for the energy production in sun and stars, but what is the reason, or what is the proof for that? How we can prove that nuclear fusion is happening in the Earth? We do not have any kind of experimental setup to go into the sun and see what is happening. So how we say that this is fusion which is happening in sun, and that is producing this energy? And this is done by observing this incoming, observing that incoming neutrino. Check that incoming neutrinos energy, which are coming from that sun's core. Number of neutrinos, huge number of billions of neutrinos are coming from core region of sun and passing through Earth's surface in each seconds. But we will not feel that neutrinos, because these neutrinos are very light particle, having very slight mass, less mass, but it is still very light particle and with a very high velocity. Okay, so these are very light particles. They rarely interact with the mass particle, other massive particles. So interaction is very small. So we cannot easily detect these neutrinos in conventional ways. So we make some setups to determine to detect these neutrinos somehow. because they are interacting very less interacting particles, because they are not having mass, which is considered a mass. So the rest mass is very small. Sometimes we feel that they are having velocity equal to the velocity of light, but then we understood that it is having very slight rest mass, and the velocity is slightly less than that of velocity of light. Okay, so observing these neutrinos, electron neutrinos which are coming out from these reactions, I'm talking about these neutrinos, and see what is their energy, and compare that energy with these calculations that we made. Then it is observed that these neutrinos, which are not coming from in that amount, okay, that if you consider the quantitatively, that amount is 1/3 of total. So when you observe that number of neutrinos coming from the core region of the sun, when you observe that from Earth, then it is observed that only 1/3 of the total what we are expecting is reaching on the Earth's surface. We observed like that. And when you consider that energy also, when you have that PP1 cycle, that energy is 0.42 mega electron volt, which is a continuous spectra. And the second case we have 0.861 mega electron volt, and third one is we have 14.03 mega electron volt for these neutrinos. So we have to measure those things. So PP1 that is 0.4 mega electron volt, PP2 0.86 mega electron volt, and PP3 we have 14 mega electron volt around. So these are the second two, PP2 and PP3 are monoenergetic, which means that only one spike will get. But the first one is continuous spectra of energy. Still, if you consider, you measure that energy, then we will get how many number of neutrinos are coming from sun's core to the Earth's surface, and then we count that number using different algorithms, calculations, all those things. We count, then we observe that only 1/3 of what we expect to come after those reactions, only it is reaching. 1/3 of that is reaching. 1/3 of the expected value. Expected total number is getting. So then we do some scattering experiment. This is just observing that energy, how much energy which we will get if you consider some particular area and absorb all those neutrons coming to that area, and check how much energy you are getting, and do some the complicated or uncomplicated calculations. Then we can say that this much of number is from that energy. Another way is that by doing some scattering experiment. Okay, scattering experiment, number of neutrinos are coming, electron neutrinos are coming, and they are scattered. We make some setup in such a way that these neutrinos are scattered. And if you have such kind of a setup, by using that scattering technique, count the number of neutrinos which are coming, then we get 60% of the total expected value we are getting. Still 30% is missing from the theoretical calculations, and these 40% is missing, and this 40% was a very great puzzle in that time, where these neutrinos are going, and we are not getting that 40% by doing these experiments. So there is the calculations were perfect, everything was perfect, but only maximum that you are getting is 60% by using that scatter. So initially by using energy technique, we are getting only 1/3 of total. Then we are getting only 60% of the total by using the scattering. Still 40% of neutrinos are missing. What happening to this neutrino? Then after 30 years, it is observed that there are 3 different neutrinos Then we need to have a different measurement system for them, different because neutrinos are different types. Then we need different kind of measurement systems for each of them, and the total number of neutrinos is found to be same as the number of neutrinos produced in sun. That means that the calculations that we have done so far in that chain reactions are right. So in that propagation, while from that sun to earth propagation, that neutrino, that is electron neutrino, we considered when it comes to earth surface, in between some of this electron neutrino is converted into some other type of neutrinos. So then when you observe that neutrino, we are assuming that these neutrinos are coming, electron neutrino is coming, and we are having some setup to detect that electron neutrino. And with that setup, we will not be able to detect these neutrinos because these neutrinos are different from that electron neutrino, and these are muon neutrino and tau neutrino. Okay, so in their propagation from sun to earth, this electron neutrino converted into some different neutrino type, so that we cannot detect that neutrinos. We were not able to detect that neutrinos initially. Then we made arrangement to detect these neutrinos also. Then it is found that whatever the neutrinos are produced by using these chain reactions and calculations that we made, they are exactly same as what we observed. So then we say that this is the reason that the fusion is the energy producing process which is happening. Okay, so we have different neutrinos now, not only the electron neutrino, we have muon and tau neutrino. And from here onwards, we will think about little more. Is there any other kind of particle exist? And if exist, what are those particles? And that we will discuss in the particle physics. Okay, so we'll stop here and we start particle physics.